So our presenter today is Chris Howarth. Chris is a registered professional engineer in BC with over 20 years experience in water and wastewater treatment. He graduated from the University of Plymouth in England with a degree in civil engineering. He has worked for both private and public organizations in Europe and in Canada, and he is currently responsible for municipal business development in Western Canada. So I pass it over to you, Chris.
Thank you, Jim, and thank you everybody for listening in on this one. So tertiary filtration using disc filters. There we go. So maybe just to get everybody on the same page to start with, these things go by different names. You see some of them on the screen here: cloth media filters, textile media filters, different ways of spelling disc filters. And then there's drum filters as well, which are kind of similar but different. So with drum filters, the actual filter media, the cloth is normally the same, but it's how it's mounted, how it's configured. So you can see from the two diagrams there, a disc filter is, as it says, a bunch of discs, hollow discs, with the filter cloth mounted on each side of the disc. And then a drum filter, the cloth is mounted around the drum. So same kind of technology, slightly different applications sometimes. Drum filters are particularly good for smaller plants, for example. So that's what we're talking about here. What do you use these things for? The most common application of disc filters or drum filters is tertiary filtration. That has been, in the past, perhaps more driven by discharge standards, effluent quality, suspended solids, and more often total phosphorus, so getting down to very good effluent quality, very low levels of phosphorus. There's also increasingly these things are being applied for reuse, and that can be, it's not necessarily mutually exclusive. You can do discharge and reuse using the same system. So I'm seeing more and more of that in BC now, people looking at this technology for reuse as well as for effluent quality. You can use them in primary applications as well, primary treatment in place of a settling process, a primary clarifier. It's a bit of a niche application, but it is being done. Drinking water as well, micro screening. So early in the process, before you get to your clarification or filtration, you can put in this kind of filter upstream of there to catch some of the bigger stuff before you get down to those treatment steps. And then there's various uses in industrial applications as well. So I mentioned reuse there. In BC, we have the Municipal Wastewater Regulations, the MWR, and in there are guidelines around reuse water, reclaimed water. And you can see a part of those guidelines extracted here. So in summary, there are 4 categories of reuse water quality in BC in the guidelines. And of those 4, 3 of them you can achieve with disc filters. The only one you can't achieve is the very highest standard, the indirect potable reuse, where you're putting treated wastewater into an aquifer, for example, just before people are taking it back out again for drinking water use. So with that kind of level of reuse, if you're looking to do that, then you're into membrane filters. But any of the other 3, which is the vast majority of reuse applications, things like irrigation, toilet flushing, spraying water in parks, whatever it might be, then a disc filter is gonna get you there. And I should say that there's also a coliform requirement in those standards, and a disc filter isn't a disinfection technology, so you will need to disinfect as well. But in terms of the filtration, the need for filtration, then the disc filter will get you to those 3 standards. So putting it into a bit of context here, what other technologies can you use for tertiary wastewater treatment? Starting at the bottom of the graph there, you see sand filters, and I should say this isn't sort of scientific, this is more just to sort of demonstrate the point. Sand filters have been around for quite a long time. They do a reasonable job of tertiary filtration, but in terms of effluent quality, they're probably the lowest on the list here. They also are relatively large, so that can make them relatively costly if you have to put them in a building, for example, or even just the basins themselves. They're quite big, and therefore capital costs can be quite high. And fairly complicated. There's different types of sand filters, so it's hard to be too general on this, but A traveling bridge sand filter is something that's been used quite a lot in this application, and it's fair to say that there's a reasonable amount of operation and maintenance that goes into that technology. Going up on the effluent quality scale, over to the left there you see disc filters. So disc filters will give you a better effluent quality than sand filters typically, and they're really nice and simple, and they're really compact as well. So in terms of the cost and complexity axis, I've put them more favorable than the sand filters. And then going up again in effluent quality, you've got microfiltration, ultrafiltration, so membranes. They give you a better quality of water than disc filters, as we were just saying there on the reuse guidelines. To get to that indirect potable, then that would mean membranes. So they do give you a better effluent quality, but with that you have some cost and complexity. They do take more operation and maintenance than a disc filter. And then right up at the top you've got reverse osmosis membrane. So you can make exceptionally good quality water using RO, but that is very complicated and pretty expensive too. So disc filters fit into a nice niche. They give you a pretty good quality of water, meeting most reuse applications, and do that cost effectively and without a whole lot of O&M to them as well. Might be worth just touching on membrane bioreactors. They're not a tertiary technology, they're a sort of complete secondary treatment process. And there's pros and cons. There's certainly a place for MBRs. I would say in some ways though a tertiary filter can be a good way to go, especially if you don't need that super high quality water, because it gives you a multi-barrier approach. So you've got the other treatment steps upstream with a disc filter. With an MBR it's more kind of eggs all in one basket. Like I say, I'm not saying they're a terrible technology. We offer MBRs in Veolia, but everything has its place, right? So disc filters certainly have their place, and they're getting increasingly popular, I would say. We're seeing some projects happening at the moment in BC, big projects where disc filters are going in. The two projects you see here on the screen, McLaughlin Point is the higher one in Victoria, the Capital Regional District, and then the new Lionsgate, or the replacement for the Lionsgate wastewater plant, the new North Shore wastewater treatment plant in Metro Vancouver. Both of those are putting in disc filters. It's I believe more driven by the desire to do an excellent quality of treatment than it is sort of purely driven by regulations, effluent discharge quality requirements by the regulators. We're seeing more of a sort of political motivation here as well. People wanting to go above and beyond, wanting to do the best possible job they can in terms of effluent quality, and then maybe leaving the door open for reuse, maybe doing reuse straight away. But certainly having that as part of the thought process, trying to keep stakeholders happy, trying to open the door to reuse. When you look at the cost of these projects, these are multi-hundred million dollar projects. They're very big projects. So adding disc filters is not that significant in terms of the overall cost. Value for money is quite high by just putting that tertiary step in. So that's maybe sort of the bigger picture. Now getting into a bit more of the details around the technology and how it works. And I should be clear now, I'm going to be talking about inside-out types of disc filters. That's the configuration that Veolia offers, our Hydrotech brand, are all inside-out. There is another way of doing it on the market. There's outside-in type of filters. So because we offer inside-out type of filters, that's what I know best, and that's what I'm going to be talking about as we go through the presentation now. So how does an inside-out filter work? Well, as the name suggests, the wastewater starts off in the inside, it goes into the inside, the influent, flows through the filter cloth to the outside. So that's what you're seeing on this diagram here. Coming in from the right-hand side there, going into each of those discs. The cloth is shown by the red dotted line. I'm not sure how clearly you can see that on your screen, but each of those discs, hollow discs, has got cloth on each side, the filter media itself. So the water has to get through the cloth where the particles are caught before getting out into the sort of basin you see there, where it goes over a weir. The reason for the weir and holding back some water, there's really two reasons. One is to do with hydraulics, and the other is to give you a stored volume, a reservoir of filtered water, because that's what's used for backwashing. So you can imagine over time, those particles are building up on that filter cloth in each of those discs. And as the particles build up, the head loss goes up, the resistance to the flow goes up. So the level rises on the influent side. And that's monitored using a level sensor. It could be an ultrasonic, or it could be as simple as a float switch. When it reaches a level set point, the unit goes into a backwash. So pretty simple. One instrument, the level sensor, two motors. So when you get a backwash triggered by the level sensor, those two motors energize. One motor turns the drum. The drum here is the sort of black rectangle you see holding all of those discs. So all the discs are mounted on a big stainless steel drum. The motor turns that drum. What that does is it takes those dirty panels out from the bottom and lifts them up to the top. And you can see on this diagram, it's about it's about half submerged, up to about 60% maximum submergence in the unit. So it lifts those panels out from the water and up to the top into the air. The other motor that energizes is in a backwash pump. That draws water that's been stored in that reservoir, filtered water, pumps it around through spray nozzles that spray water from the outside of those discs, and that knocks off the material that's built up, the sludge that's built up on the inside of those discs, and it gets collected in a trough and flows out by gravity. So pretty simple. There's no actuated valves in here. The only valves on the system are manual, so very simple, and you don't need to operate them to do a backwash. So this is a photograph showing you the idea. You can see as those discs are rotating past those spray nozzles, the material's being cleaned off, and you get nice clean panels on the other side of those spray nozzles there on the manifold. It is very simple. Here you see the P&ID. P&IDs are always a little complicated, but when you look at this and sort of get into it, you'll see that it's actually about as simple as a piece of equipment can be in terms of a P&ID. As I said before, one instrument, two motors, a few manual valves, a few pressure indicators, pressure gauges, but really not much to it. The other thing you see on this P&ID, aside from the influent, the effluent, and the sludge, is cleaning chemicals, and I'm going to come back to that. That's an important point. But before we get there, just to look a little bit deeper at the backwashing components. So at the top there, you see the manifold with all the spray nozzles on it. That's on a sort of swivel joint, so if you need to get in there and change a nozzle, for example, then it's very easy to get to, just swivels out, and then you've got full access to it right there. You can see the trough underneath as well. If you look closely on that photograph, you can see the sort of slots in that drum. That drum is what's holding all of those discs, and each of those slots goes into the discs. So that gives you a sense of how the sludge comes back out. Something we did about 5 years ago now was introduce self-cleaning nozzles. So it's always good to get operator feedback, and something we were hearing is that those nozzles were blocking, and it was a bit of an O&M task to have to get in there and unblock the nozzles with a toothpick, typically, about a 1 millimeter jet on the nozzles. So it was something that took some time. When you think about it, the actual filtered water that's going through those nozzles is filtered down to, or typically 10 microns. It's a sort of cloth mesh opening. And if you've got a 10 micron filtered water and a 1 millimeter jet, then it seems strange that it would block. But what you have to remember is that this is wastewater. So stuff grows in those pipes, in all that manifold and piping. So over time, a bit of biological growth, a bit of biofilm kind of stuff growing. It's going to get sloughed off every now and again, get into those jets, and that's what's causing the block. So the self-cleaning nozzle avoids the need to have to unblock things. And how it works is if you look at that photograph in the middle, you can see the actual jet itself there, and it's kind of split. You can see like a line going down the middle of that jet. One half of that is fixed. The half on the left is fixed as we're looking at it here. The half on the right is held open by a spring, but when the pressure comes on, when that pump fires up, pressurizes the system, that spring force is overcome. So that moving half slides forward, closes down the jet, and then of course when the pump depressurizes, slides back out, lets anything that might have blocked in there come loose. So self-cleaning nozzles really do away with that need to have to unblock jets. Chemical cleaning. So I said I'd come back to this. The chemical cleaning manifold is separate from the backwashing manifold. So you can see here there's the chemical manifold is across the top of the unit on that big photograph in the middle there. Separate nozzles connected to a chemical dosing pump, which is connected to a batch tank. Our cleaning system uses very small amounts of chemicals. So you're not looking at a big tank, maybe a few tens of liters typically. So how it works is you're going to prepare a batch of cleaning chemical. Bleach is a common one, sodium hypochlorite. Dilute it down to a few percent, 2-3% typically, and then Through the control system, you're going to have a screen, automated chemical cleaning screen. You know, press the green button on the do a chemical clean, and then after that, it's all fully automated. How it works is you get that dosing pump sprays a little bit of chemical through those nozzles onto the panel, and you can see there's sort of pie segments. That's how it's divided up. So it's going to spray it onto one of those pie segments on each disc down the row. Lets it sit for a minute or two, steps to the next panel, sprays a little bit more chemical. So it's doing this, it's soaking the chemical onto the filter cloth, but because it's in the air, it's out of the water, that means you only need a very little bit of chemical because it's effective in covering the cloth. Also, very importantly, that means you can keep the filter online while you're doing a chemical cleaning. This is not possible with the outside-in design. This is a feature of the inside-out design, that you can keep the system online, the filtering, because you're putting such little chemical into, to do the cleaning, that is not a problem in terms of discharging chlorine. It's going to get neutralized because there's so little of it, and there's such a lot of dilution going through, and other things that are going to bind up that chlorine before it goes out into the river. So it's definitely a feature, and when I say very little, we put in a system recently, I'll talk a little bit about later. It was a 25 megaliter a day plant, design flow for the filters, and there we were talking about less than $50 a year in chemical cleaning costs, the chemicals, less than $50 a year, so next to nothing. I should say also, in tertiary wastewater filtration, you are going to need to chemically clean sooner or later. It's wastewater, things grow in there. So the most common need for cleaning is the bleach to get rid of organic growth. Some other reasons for doing it could be if you're using ferric, then you can get some iron type scales forming. If you're in a hard water area, you can get calcium and magnesium scales forming. But for sure, sooner or later, to maintain filtration performance, you will need to chemically clean. Varies from about every few weeks to every few months. So the filter media. We use a woven polyester cloth. We've been using it for a long time, you see, since the 80s. It holds up really well. We've got, as you can see, a lot of experience of a lot of time using this cloth, and it's proven to be very durable. We actually guarantee it for up to 20 years, which is longer than any other manufacturer that I'm aware of. We offer it in a range of openings, the actual weave, tighter or looser, depending on the application. In a tertiary treatment application, it's often we're going to be using the 10 micron cloth, the tightest mesh size. Could be a little bit bigger than that. I see 40 micron sometimes, for example. Another reason for using the woven polyester is that it results in quite a thin cloth. It's a little bit like a bug mesh. So when you spray that backwashing water onto it, then it's really effective in removing the sludge because it's quite a thin cloth. Some of the other filters on the market use a much deeper, thicker cloth, a bit like a carpet. So maybe that's perhaps harder to clean, I don't know, but certainly in terms of the thin woven polyester cloth, it's very effective for the backwashing. It's very easy to get the sludge off it. It's also chemically resistant to things like chlorine or weak acids. Hydrochloric acid is what we would normally use for getting rid of those calcium or iron scales, for example. So it fits the application very well. There's quite a lot on this slide. I won't get into too many details here. This is perhaps more for the engineers in the audience than the operators. But a few sort of design features, considerations when it comes to how you design around this equipment if you're installing it. It runs at a low head loss, so that backwash is typically triggered at around about 250 millimeters. So that's the maximum head loss you're going to see through the filter cloth. It's not a whole lot of head loss for the unit. Because it's only partially submerged, you don't need to have they don't get installed very deep, so if you're doing excavations, you don't have to go down too far. With our design, the inside-out design, the Hydrotech system, it's fully assembled when it arrives on site and tested before it leaves the factory. So that's another feature of the inside-out. You can put everything sort of on the frame, whereas the outside-in, that's normally not the case. You'll have a separate pump gallery, and you're going to have to do some on-site installation of pumps and valves and so on. They're also offered with a stainless steel tank, so you can put it in concrete. You see that on the bottom diagram there. And then on the bottom right, you see a tank version. So that's an option. If you'd rather have it piped, it can be less for the contractor to do on site on the install, then that's an option as well. Another question I get quite often, if you're doing disc filtration, do you need to chemically pre-treat the wastewater before you filter it? So this is separate from the chemical cleaning, this is chemical conditioning on the actual wastewater. And the answer is maybe. So looking at the particle size distribution diagram you see there, this is a result that the folks in Banff shared with us to give us an idea as we were starting to look at this project of how filterable the sludge was leaving their secondary clarifiers. What did the particulates look like leaving in the secondary effluent? You can see on this particle size distribution, and this is a log scale by the way, so on the right you've got 1,000 microns, that's 1 millimeter. Most of the material, most of the particles is up there. Going down, getting down to as low as small as 10 microns, you can see it basically tails right off. There's very little material down around the 10 microns and basically nothing below 10 microns. So we'll look at that and we say, well, we've got a 10 micron cloth, we're going to basically catch the majority of it. So doing a particle size distribution can be a good idea to give you a sense of how filterable your water is. If that particle size distribution had looked different and there was a whole bunch of stuff down around 10 and smaller, then chemical preconditioning would probably be a good idea using polymer to flocculate those fine particles into bigger flocks that are then going to get caught on the filter cloth. So polymer is something you might need to do in some applications to help you get better filter performance. The other thing you might need to do in terms of chemical conditioning is if you're trying to remove dissolved substances. And in municipal wastewater, that normally means dissolved phosphorus. So in that case, anything dissolved will go through any filter. So you then need to precipitate it, and you would do that using coagulant. So those are really the two reasons you might need to do chemical preconditioning. Getting a little bit maybe into the O&M now. Something I love, I'm a sales guy. I talk with folks about the options with the benefits of our system, and one of the things I love when I talk to existing users, existing operators of our equipment, is that they say really nice things about it. Fortunately, there's not many folks in the room here because this might be a bit contentious, but what I often hear operators saying is that there's normally constructive feedback. There's always something that could have been done a little better, and that's great. That's useful for manufacturers to get that feedback. But by and large, we're folks who run the Hydrotech filters, they really do say nice things about it. This is an honest quote that a guy said to me. He said he loved his Hydrotech filters, and I really don't hear that very often from operators. So I'll stop there. I'm not getting anything thrown at me yet. So yeah, they work well. People like them. It's partly that inside-out thing. When you open the lid and you've got to work on a nozzle or change the drive chain or whatever it might be, you're in clean filtered water, much more hygienic. Less wear on those mechanical components, on the seals and all of that. So they hold up pretty well, pretty reliable. And you never take these things offline, basically never. Okay, I'm not going to say never. It's about every 10 years. You'll see the maintenance frequencies coming up, but it is very, very long frequencies between having to drain those basins. They are always online, whether you're backwashing them, chemical cleaning them, they are filtering. So that's also a great benefit for folks who are trying to run a treatment plant. So what are the things you're going to have to do to look after this equipment? It's a good idea to go in and check on it from time to time. We would say at least every week. If you're doing a daily walk around as part of your schedule, then pop into to have a look at the filters. It's certainly not a bad idea. Hang around there long enough to hear the thing go into backwash. They normally do that a few times an hour. So is the pump making strange noises, for example? It's that kind of stuff, right? Just keep an eye on it. It's kind of obvious, I suppose. You might need to do a little bit of maintenance on the level sensor. If you've got a float, then maybe give a little spray clean, get the sludge off it from time to time, ultrasonics, keep them clean, that kind of stuff. And sooner or later, you are going to have to replace filter media. As I said earlier, these things last a very long time, but sooner or later it's going to fail. So have a look at that, inspect it. If you do need to replace filter media, you're going to see that because it's going to get torn, basically. It's going to get worn out, and then it's going to tear. So as I said before, these filters are designed with the media in segments. To remove a segment, it's got one bolt. The cover is on a loose hinge, so you get that bolt off, and then you can just take the whole cover off. Then You slide out the filter segment, slide in a new one, put the cover back on. You can do that in less than 2 minutes. You can do that without taking the thing offline. So these are the maintenance frequencies. There's quite a lot to read through here. I'm not going to go through it all. Basically, it's the typical stuff. It's greasing, it's it's bearings, that kind of stuff, seals. But when you look at this, the actual frequencies of replacement are very long, 10 and 20 years. So if you're having to replace a seal, yes, you've got to take the thing offline. You're going to need to drain the basin. But those happen over very long frequencies. Nothing particularly challenging in terms of maintenance. We've put in a bunch of these. I believe we're the leader in the world in terms of installations, over 11,000 units now. Lots in North America, lots in Canada, and some of the biggest in the world. I'm pretty sure that the one in Egypt there, which is currently in construction, 5.1 billion litres a day, that's a big plant, right? So I think that's the biggest in the world now. Canadian municipal installations, what we're showing here. There are 1 or 2 in BC. The ones in italics there, so that's Calgary, Cultus Lake and Lake Country, those are selected, they're ordered, but they haven't been installed yet for various reasons. These have been pre-selected kind of early, but the others are delivered. Just to touch on a project, so I mentioned Banff earlier when I was talking about the particle size distribution. This is a nice project just to give you a sense of it if you haven't seen these kind of things before. Travelling bridge sand filter is what you see on this photograph. It's been in a few years, over 10 years, but it wasn't great. The city wasn't very happy with it. They were struggling to get good quality effluent. It was taking quite a lot of operation and maintenance. Flies in the room. It was just not great. There was a lot of things about it that they weren't really very happy with. So they bit the bullet and decided to upgrade. They have 2 of those filters. They took one offline, so filter 2 is still there, but it's kind of mothballed. Filter 1 is what they offered up to do the upgrade. And you can see here, 2 disc filters fit into that basin sideways on, perpendicular. So we increased the capacity, we improved the effluent quality, and we did that in less than 1/2 of one of their existing basins. So that just shows the sort of compactness of this technology. This is how the installation looked. Not a whole lot to see there. Something a little unusual on this project is they put in a steel wall. They did that because the municipality wanted the project to go at a very, very fast pace. The contractor, it was done as a design build, and the contractor was incentivized to have this thing offline for as little possible time. So that's why they put in a steel wall. But other than that, it's a pretty typical installation. Very easy to do in terms of channel modifications. There really wasn't much to it. It fit in the existing hydraulic profile, so really very simple. The entire project came in at about $1 million, and that was the full design build cost, so everything installed. Of that, the filters are about half of it, so very cost effective. As I was saying earlier, in terms of value for money, these filters give you good value for money. Another photograph, just a little bit closer picture of one of the filters there. So going into this, the town of Banff had performance criteria in the design build RFP. So you can see those on the top 2 rows of that table there. One of those was an annual average. So what they were saying is that over the course of a year, we're going to give you no more than 15 milligrams a litre TSS in the feed to the disc filters, the secondary effluent. And with that, we want you to give us an effluent back, annual average of less than 3 milligrams a litre. That's a pretty tight number. That was, it didn't make us feel too comfortable, I'll be honest with you. That's the limit of what we would guarantee. That is right at the limit of this technology, 3 milligrams a litre effluent. They also had a daily number, so less than 25 in any one day, and then we were expected to meet less than 8 in our effluent. We did the performance testing. It was a 24-hour composite sampler we were using, so off to an external accredited lab. It was, very robust kind of performance test. And you can see that actually they gave us 33.5 milligrams a litre. I think they deliberately challenged us a little bit, actually. I think they put a bit of sludge in there or something, because that's pretty high. That's not typical for them. And then we gave them below detect. The accredited lab had a detection limit of 1 milligram a litre TSS, and it was below that. So pretty good results. Everyone was really happy with that. We were even a little surprised, if I'm honest with you. That's a good number. Just slightly a few words on a new filter that we've recently introduced. And I say new, it's more of a refinement. Where the rubber hits the road, the filter cloth has not changed. So in terms of the performance you can expect, the longevity you can expect, that doesn't change. It's exactly the same filter cloth that we're using, but we've kind of tweaked lots of things around it. In the mechanical design of the filter is what we've worked on here. Call it the performance filter. So what have we done? What improvements have we made? One of the main ones is we've put each of those discs closer together. We did that by redesigning the backwashing system. So you saw earlier the manifold, we've kind of just squeezed everything up. Those nozzles are tighter, so that means we can get those discs closer together. If you can get the discs closer together, then you can treat more water in a given volume, in a given footprint, because you've got more filter area in that given volume. So it makes the overall unit smaller. That's good in terms of footprint. If you've got a tight side or want to build a new building around it, then smaller building. It also is good because a smaller unit is generally a cheaper unit, capital cost savings. Where you've got relatively high flows and you need multiple disc filters to be able to treat those flows, then you might save yourself a filter or two because you can pack more filter discs into a given unit. Even the very biggest unit now is able to treat much more water, so maybe you don't need 3 of them, maybe you now need 2 of them, for example. And that means less O&M because you've got less of the backwash pumps and all the rest of it. By tightening up those discs and changing the design of the backwashing system, we're able to make the backwashing more efficient. The spray nozzle is closer to the filter media, so we can run at lower pressures, we can use less water, and if you're doing that, then you're going to save pumping energy and you're going to make less sludge. The sludge will be thicker, which is a benefit. So, like I say, a sort of mechanical design improvement that has these knock-on benefits in various terms: footprint, capital cost, operating cost. Another thing we did, this is from the marketing team, Pegasus. I'm not sure if I like it or not, but they tell me it stands for Particle Guidance System, so make of that what you will. But how I look at this is thinking a bit like, what's the sludge doing? So when that particle comes in with the influent, firstly, how do you catch it? How do you catch as much of it as possible, as many of those particles as you can? And then where does it go from there? When you're into the backwashing, how do you ensure that sludge gets back out again as efficiently as possible and obviously out with the sludge stream? So thinking like that resulted in us making a few design changes. We changed the design of those segments, how they fit into the disc, so how they're retained. We basically had less material blocking the filter cloth. So the segment is basically the same size, but if you've got less stuff around it holding it in, then you've exposed more of the cloth to the flow, and that means you're more efficient. You've opened up more filter area. Less sludge retention in the disc is to do with how the sludge comes back out again during a backwashing. So by ensuring that when that stuff is sprayed off the cloth, that it gets out very efficiently. Otherwise, before it was less optimized, and that meant that there was some sludge that even though we'd sprayed it off the cloth, it hadn't got back out into that trough that you saw earlier. So ensuring that it gets out. And then the trough itself, ensuring that it catches all of the sludge that comes out as opposed to the sludge being able to kind of escape out of the trough. So all of this resulted in an improved backwash design, a more efficient sort of particle management, if I can put it like that, and that also helps with this new performance filter to do a better job of treatment, more efficiency. Give you a sense of what this means. So pictures that tell 1,000 words, I guess. So you're looking at the older one on the left, the HSF, and that's a 2224. The 22 means 2.2 meters diameter, so those discs are 2.2 meter diameters. 24 means there's 24 of those discs mounted along the unit, and you can see that on the cross section there on the top right, 24 discs in the unit. The other one, the HPF 2244, so you can see in terms of the unit size, it's a little bit longer, but not a whole lot, right? Still 22, so still 2.2 meter diameter, but 44 discs now mounted in that unit. So a tiny bit longer, but almost twice as many discs. That doesn't give us twice as much area. It actually gives us more than twice as much filter area because of those other things I was talking about earlier, getting more of that cloth exposed, the Pecos thing. So the older unit, the 2224, has got 134 square meters of filter area in it, filter cloth. The newer unit, the 2244, has got 271 square meters, so more than double the filter cloth area. So I think we're just coming up for time now, but there is a bit of time for questions. So firstly, I'd like to thank you for your attention and your interest in joining this presentation. And then if we've got questions, maybe Jim, you'd be able to
Yeah, thank you very much, Chris. We do have a couple questions come in. The first one is from Ben. What is the source for table 13? This came in early, so it's right at the beginning.
Okay.
Of your municipal effluent quality requirements for reclaimed water.
Oh yeah, yep, right, got you. Where is it now? Getting there soon. There. So this is the Municipal Wastewater Regulations, BC Ministry of Environment, MWR, Municipal Wastewater Regulations. And in there, I think it's section 7, if I remember rightly, of the MWR Reclaimed Water Guidelines. That's where that table comes from. So a direct sort of extract from there. It's available online. If you get into Google and type BC Ministry of Environment, Municipal Wastewater Regulations, Reclaimed Water Guidelines, then it should get you pretty much straight to it.
Okay, thank you. The second question, where would the membrane bioreactors fit on the tertiary filtration sweet spot chart?
Yeah, I think the honest answer is they don't really fit on this chart because they're not a tertiary treatment technology sort of per se. What I've shown here is filters, different types of filter. A membrane bioreactor is a system that uses a membrane as a clarifier, really. An MBR, the reason for the membrane is partly to give you very good quality effluent. So like that, I guess you could see it as, you know, it gets you to tertiary quality, no doubt. But the membrane is also there as part of the overall secondary treatment process, the clarification of sludge to be able to recirculate that sludge back into a bioreactor. So MBR, membrane, bioreactor, it's two things really. It's a membrane for clarifying and filtering, and it's a bioreactor for doing the biological treatment. So I'm not sure if it would really fit. I mean, arguably it probably fits in the MFUF box. An MBR typically uses a microfiltration or ultrafiltration type of a membrane. So it probably fits around there in terms of effluent quality and arguably in cost and complexity as well. But to be clear, a disc filter is not, it doesn't do the same amount of work as an MBR, so it doesn't really fit on this chart.
Okay, thank you. John has a question here. How long before you have to replace filters, and how high of TSS can they handle and for how long? So what's kind of your maximum loading?
Yeah, good questions. So how long does vary between different manufacturers. I mentioned before that we have offered filter cloth guarantees up to 20 years. To be clear, that's a pro rata guarantee. It's a lot like a membrane guarantee, if you're familiar with those. So what we mean by that is that by the end of 20 years, you will have had to have replaced all of your cloth. If after 10 years you have had to have replaced all of the cloth, then we will pay for half of the filter replacement cost because it only lasted half as long as we said it would. And I should be clear that that is application specific. We're not necessarily saying for any application we're going to guarantee 20-year filter life, filter cloth life. It does vary between applications. The other part of the question, sorry, was TSS load.
Maximum TSS load.
Maximum TSS load. So how these filters are designed, certainly how the Hydrotech filters are designed, is based on TSS load. You have a filter area. You are able to pass water through that filter cloth at a specific rate, meters cubed per meter squared of cloth per hour, based on the amount of TSS in it. So TSS load is a key design parameter that we need to know to be able to size the filter. Bottom line is the higher the concentration and the more flow you have, the more flow you have, therefore the more load, the more filter cloth you're going to need. So in theory, there's no limit to the amount of TSS you could put into these things. Certainly in primary treatment applications, for example, we design around hundreds of milligrams a liter of TSS. In a tertiary application, which was really the main subject of this presentation, you're treating secondary effluent. So there you're into a TSS concentration, maybe 20, 30, up to 50, something like that is typical in that application.
Okay, we've got another question here from Pat. She was asking, what does the facilities do with the sludge coming off the disc filters?
Yeah, so the sludge is typically, given that it's a tertiary application, you're going to send the sludge back to earlier in the plant. If you've got primary clarifiers, it's probably a good idea to send it back there, or certainly secondary clarifiers. You wouldn't want the sludge to go into too much of a closed loop, so when you've taken it out on the disc filter and put it back in before your clarifiers, you can remove it in the clarifiers. So that's really, that would really be the place to put it. Yeah, it could go to your sludge stream, but probably to put it in the clarifiers, then it's going to come out a bit thicker than it would.
Yeah, go thick. Yeah, I agree with that. Okay. Okay. Just I have to look at the chat. Okay. Well, I think that's it for questions, Chris.
Great. Thank you.
Again, EOCP would like to thank you for your presentation, and we've got a little lunch bag here for you for the thank you.
Oh, great.
Cold fed.
Well, thank you very much.
There we go.
Yeah, thank you, everyone. Thank you, EOCP.